So a big part of working with probabilities is calculating, how many possible events are in your sample space. That amounts to counting procedures quite often. And we're going to start with a very basic one. In fact, if I look at the row just in front of me, there's 4 people in the first seat, or there's 4 people in this row. So if I was to try and arrange you in different orders, let's see how many different orders that I could choose. How many different ways can I put these 4 students in order? Well, I have 4 people that I can choose for the first seat here. And then once I choose somebody to sit in the first seat, then how many choices do I have left for the second seat? 3, and then 2, and then 1. Now, in a math class, this is called 4 factorial. What would this be in an English class? 4! All right. I like waking you guys up. it's my standard one-liner here. But 4 factorial is a convenient notation. It's the number of ways you can arrange a group of 4 objects. And in general, n factorial is n times n minus 1 times n minus 2, etc. All the way down to 3 times 2 times 1 is the number of ways you can arrange a collection of n objects. Of ways you can arrange a collection of n objects. Now let's find that key on our calculator and experiment with it a little bit. In fact, maybe I can pull it up on Google Sheets as well. So I think we can do it there. So on our graphing calculators, you're going to find it underneath the math menu. So let's see here. Let's do a simple one to start out with. Say even a modest number like 10. 10 factorial is going to get pretty big. You have to type in the number 10 first. So type in the number 10. Then go to the math menu. So press the math key. And even then you're not quite done, because we've got to go over to probability across the top. So you press the math key on the left-hand side, third button down underneath the second button, and then use the arrows to go over to probability. Does there look like there's anything promising at this point in our menus? 4th option down. So type the number 4 or cursor down and press enter. That'll give you 10 factorial. And there's a surprisingly large number of ways you can arrange a group of 10 objects. 3.6 million different ways you can arrange just 10 objects. Or if you had, if you wanted to do 9 factorial. So 9 factorial. So if you lined up the starting lineup of a baseball team, there's 362,880 different ways they can stand at attention for the Pledge of Allegiance at the start of a game. It's a lot of different arrangements given such a modest number. And this factorial number is something that grows really big, really quickly. Now, I don't think I'm going to take the time to open up Google Sheets, but the command in Google Sheets, for those of you who happen to have it open, is fact. So you would type in equals and then fact, and then type in whatever number n that you want. So let's look at something a little bit bigger. 52 factorial. Where would the number 52 be familiar from? Deck of cards. So how many different ways are there that you can have a deck of cards, a deck of well-shuffled cards arranged? Well, a lot. A lot. A lot is a pretty good description here. 52 factorial, so go over to probability. 4th option down. 52 factorial. Whoa! So I'm getting this 8.0658 E67. Remember, that's a number in scientific notation. So it's times, really means times 10 to the 67th power. So if I wanted to write this out in decimal notation, I'd probably have you guys do it. No kidding. You'd have to move the decimal 67 places to the right. That'd be a huge number. I was thinking about that on the way to class. It's probably likely that there are different orders for a deck of cards that have just never been shuffled in all of human history, because that's just such a colossally large number. All right. Now, a lot of times, what we want to do is not just arrange a group of objects in order, but we want to select a certain subset of those out of a collection of n objects. And that's going to turn into something called combinations. So, combinations. Now, before we do combinations, let's just do one. Let's go back and do one probability problem first. And it's problem number 18. My bad. Says the author currently has 7 different books in print. If those 7 books are stacked in a random order, what is the probability that they're arranged in alphabetical order from top to bottom? So, kind of nice because it pulls together a couple things. It pulls together probability, and it pulls together something we just did, which is calculating different orders. So if you have 7 books, how many different ways are there that you can arrange 7 books? Yeah, 7 factorial, right? So now, out of those 7 factorial different ways, how many are there that are in alphabetical order from, what do you say? Arranged out, yeah, from top to bottom. There's only one. There's only one way that's in alphabetical order. So the probability here is 1 over 5,040. So probably not real good odds if you're gambling. Combinations are where it gets a lot of fun. So combinations. So N choose R is the number of ways to choose R objects from a set of N objects and let me put this little note here, and it's really rather unimportant, but I'll just underline it anyways. When order doesn't matter. So that is, doesn't matter if you pull something out first, last, in between, doesn't matter. The order just doesn't make a difference. Like when they're choosing lottery numbers. You don't have to match the super lotto in the order that they draw it. If you have the right number, it doesn't match, or doesn't matter what order it was drawn out. It just matters that it matches. So I'll show you the formula for this, although the good news is that you're actually not going to have to use the formula itself. So the formula N choose R would be this. N factorial divided by R factorial times N minus R factorial. So that's the actual formula for this. Now, sticking with our card playing example. Typical poker hand is 5 cards. Let's calculate how many different ways there are to choose 5 cards out of a well-shuffled deck of 52. So in this case, it would be 52, choose 5. And it's going to be huge. Any guesses? You should get about 2.6 million, a little bit less than that. But let me show you how to find that on your graphing calculator, and then I'll also mention how to do it on Google Sheets. So, type in the number 52 first. You got to type in the N first, and then make your way over to the math key, like we did before, Where do you think I'm going to go from here? Probability. So cursor over to probability. Does anything look promising from the probability menu? Third option down. Now, yours might look a little different than mine. If your operating system isn't the latest and greatest, that's fine. 52 choose 5 should still give you just under 2.6 million. Yeah.
I was just going to say, you can choose that before you type in either of the numbers, and then you can fill in the boxes.
Oh, can you? Oh, okay. You know, that's interesting. I've never done that. So let me take a look here. Let's go to probability. Oops, I didn't want that one. Probability. Oh, okay. So 52 choose 5. Yeah. Okay. Didn't realize you could do that. Hey, pretty cool. So 2598960. So, like I said, just under 2.6 million. Now, in poker, there are 4 royal flushes. There's 4 different types of hands that are called a royal flush. It's the highest hand you can get in poker. So your odds of getting a royal flush off the first 5 cards of a well-shuffled deck would be 4 divided by that. So, again, you can use this in the calculation of probabilities. It's very, very useful. Now, one thing that we have to keep this straight with is something called permutations. Permutations and combinations. They sound similar. They're going to look similar in terms of their calculation. I did promise you how to calculate this in Google Sheets. So in Google Sheets, the calculation is equals combin of n comma r. So if you type that in Google Sheets, you'll get the number of combinations of r objects chosen from a set of n objects. Now, what's the important assumption about combinations here? What was it that they just underlined? Order doesn't matter. Sometimes order does matter. If you're selecting, people from this group to be, say, the class president, class vice president, treasurer, secretary, order does matter. President, not president, order does matter. Just ask Hillary Clinton. So, all right, cheap shot, sorry. What happens when the order matters? Well, then you're going to calculate permutations. Permutations. This is going to be the number of ways you can choose R objects from a set of N objects when the order does matter. NPR, not National Public Radio, although that's kind of cool. The number of ways to choose R objects from a set of N objects when the order matters. And again, let's emphasize that the order makes a difference here. Now the formula, and we're not necessarily going to actually have to use a formula, but the formula is this. You're going to take n factorial and divide it by n minus r factorial. So a little bit less involved than what you have to do for combinations. So let's go back to our card example. What if the 5-card hand you were dealt, what if the order of the cards made a difference? How's that going to affect the number of ways you can do this kind of calculation? Well, if the order makes a difference, that's going to make a huge difference in the number of possibilities here. So let's do 52 permute 5. Hope this doesn't go beyond the limits of my calculator. I don't think it should. It should probably be up to something to the 69th power or 70th, I would guess. So going back to your suggestion, I think I can type in the math and over to probability. This time I want the number of permutations. So 52, choose 5. So yeah. So 3118 75 200. So wow, you've jumped from 3.6 or from 2.6 million up to 311 million. So it's a huge increase in the number of possibilities here. Wow, it's a lot. Yes, please.
I was just curious, just looking at the formulas. So if you were to take the NCR and multiply that by R factorial, would you get the NPR?
Yes. Yeah. Yeah. So what's happening is let's try and take a kind of a small example. Suppose you have, say, 7 objects and you're going to choose 3. So 7, choose 3. Well, you're going to have your 7 factorial. That's the number of ways you can arrange 7 objects. But we're really only choosing 3 of these. So 7 times 6 times 5. That's the way you can choose your 3 objects. But if the order doesn't matter, then you got to divide out by the number of orderings of those 3 objects. So that's your 3 factorial. If you're to calculate 7 choose R, it's going to be 7 factorial over 7 minus 3 factorial times 3 factorial. And what this part does is it cancels out all the rest of that. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. This is your 4 factorial, and then the 3 factorial. So that part that you were just talking about cancels out that. So you're right. So that's the difference, though. This is the number of different ways you can arrange those 4 objects. So that's why that little piece is getting canceled out. So thanks for the question. Your big challenge in this section is going to be figuring out which one of these to use. Yes, sir? Correct. Correct. So let's take a look at a couple problems, starting with problem number 20. So in the Illinois Little Lotto game, you win the jackpot by selecting 5 different whole numbers, 1 through 39, and getting the same 5 numbers in any order that are later drawn. What is the probability of winning the jackpot in this game? So I'm assuming you're going to buy 1 ticket. So that's going to be in our numerator. So probability of winning, is going to be 1 over something. The question is, what's that something? How many different ways are there that they could pull the numbers in this lottery? Well, let's see. They're selecting numbers, what? 1 through 39. How many are they selecting? 5. Now, the big question I want you to answer, don't shout it out yet. Answer to yourself, does the order matter? Do you have to match these things in the order that they're pulled out, or is it enough just to match them? Now, with your answer, turn to a neighbor and discuss it. Discuss, should we be using permutations or combinations? But turn to a neighbor and try and convince your neighbor that you got it right. All right, go ahead. It's your chance to actually socialize with somebody other than Siri. So take advantage of it. All right. So what's the consensus? Do we have to match this in order or no? No. Thank God. So otherwise it'd be a lot more difficult. It'd be 120 times or 5 factorial times more difficult. But your probability of winning then is going to be 39 or 1 over 39 choose 5. So again, that's something you're going to do on Google Sheets or on a graphing calculator. So 39 math over probability, choose 5, still pretty big. 575,000. It's kind of a neat number, really. 5, 7, 5, 7, 5, 7. Yeah, pretty cool. So 1 over 5, 7, 5, 7, 5, 7. So not too bad. Certainly better than your chances of winning the super lotto, which are really, really slim. But kind of fun to dream about what you're going to do with all that money. All right, so are you comfortable with the conclusion then that the order doesn't matter here? All right, that's good. Let's just look down at, and you have to forgive me for this. My deepest apologies. We're going to do one of your homework problems. Please don't, rip on me, go out on Rate My Professor. Yeah, you always used to do our homework problems. I hated it. Well, let's take a look at problem number 21. This is kind of nice because it blends a few things. The Technomill Corporation must appoint a president, chief executive officer, chief operating officer, and chief financial officer. It must also appoint a planning committee with 4 different members. There are 12 qualified candidates, and officers can also serve on the committee. So, first question is, how many different ways can officers be appointed? So, this is getting to the idea of, does the order matter or not? If you're going to be an officer, does it matter if you're picked first, second, third, or fourth? Yeah, it does matter, because CEO is different than COO, different than CFO, etc. So in this case, the order matters. So if the order matters, what should I be doing for my calculation here? Permutations. Good. So I should do 12P4. It's going to be pretty big. 12P4. So I'm getting 11,880. You guys be able to match that calculation? All right, good. So 11,880. How many different ways can the committee be appointed? Does the order matter here? No. So this time it's 12C4. So 495. So a lot less in terms of the number of ways that a committee could be appointed. Last but not least, what is the probability of randomly selecting the committee members and getting the 4 youngest qualified candidates? So another probability question here. We've got the 4 youngest candidates. Well, how many ways are there to get the 4 youngest candidates? It's only one, right? It's only one way you can get exactly the 4 youngest candidates. How many possibilities were there? I'll give you a hint, you just calculated it. Yeah, 495. So 1 divided by 495 for this last one here, problem 21. Any follow-up on problem number 21? Good there? There's a couple other different counting rules that can come into play. They're all summarized for you on page 176. Let me tell you the ones that I'm not going to be emphasizing. So we've done these two counting rules, permutations and combinations. Actually, pardon me, these two, permutations and combinations. Where is it? No. 1, permutations, when all items are different. Yeah, 3 and 5 we've done. And then we did the factorial rule. Now there is kind of a fundamental counting rule, and that is when you have different events that can occur in m ways for one and n ways for another, then it's going to be the product. So for instance, if you were rolling a single die, you have 6 different possible events, and then tossing a coin. Together there's 12 different events, so it's a different counting rule for that. You'll see that here and there. What I want to emphasize now is the permutation and combination rule. So let's do a couple more for that. Let's look at the Powerball calculation. And this is kind of getting at that last little bit here that I was talking about in terms of products and multiplication. Powerball is run in 42 states. Winning the jackpot requires that you select the correct 5 numbers between 1 and 59. And in a separate drawing, you must also correct the correct single number between 1 and 39. So the product of these two is going to be the number of different ways you can win, or number of different ways you can choose a winning number. You know what? I didn't realize that wasn't on the screen. So let's start with this part. You have to match 5 numbers chosen from a set of 59. Are you going to have to match these numbers in order or no? For the lottos? No. Thank goodness. All right, it's tough enough as it is. So if you don't have to match them in order, which of these things are you going to use? Permutations or combinations? Combinations. So it's going to be 59, choose 5. And that's going to be a big number. But it doesn't stop there, because then you also have to match a number chosen as the Powerball, right? So for everything here, how many choices are there for the Powerball? 39. So it's going to be this colossal number times 39 should give you the number of different ways you can win, or different ways you can draw your number for the Powerball. So let's find that number. So 59, math, and then probability, choose 5, oops, 9, 9, choose 5. So that's pretty big. Now we need to multiply it by 39. $192, excuse me, 195, 249, 054. Wow. That's a big one. If you have one ticket, what's your probability of winning? Yeah, basically nothing. Actually, 1 over 195,249,054. Yeah, pretty small. But hey, somebody's got to win. All right, let me stop here and give you some homework to try. I realize that we've done a couple of these in class, but you might want to look over them again in homework as well. So for homework, try 3 through 23, and then let's see, 31 and 33. That's section 4.6.